above only, so you have like a leaf that just has this discontinuous point because there's another leaf floating in, things like that.
Would point cloud completion stuff, would that help?
I need to try that. I haven't tried that yet. But it would help because like one of the things we need to do is just like semantically segment it so you're grabbing only the point cloud of interest. There's generally like 5 per plot, but we only care about 1.
Interesting. It's a cool problem. All your data is point cloud.
They have a lot of other things as well. So top-down images, thermal, a couple other things that I don't know the name of right now.
See that multimodality things? Interesting.
Yeah, I mean, if you could register the RGB to the point cloud, the problem is most of it's not taking at the exact same time.
It'd be really hard.
Yeah. But if you could do that, then it's easy because it's like, okay, everything that's brown, we don't care about that.
We had to a lab had to go through an image registration effort with like 130 video clips from IR, from different bands of IR. So, oh my god, like why would I do this?
Did you manage it?
I put that shit off. I was like, I ain't doing this. I have more important things to do.
Yeah, I've been kind of doing the same thing where we're talking about doing registration between the RGB and the point clouds. I'm like, oh my god.
Yeah, this is going to be such a pain.
Yeah, it sounds hard.
It sounds like some undergrad could do it.
So there are a lot of people in your lab working on vision problems?
We have 1, 2, 3, 4. We have 5 PhD students currently. 3 of us are working on a joint effort. It's like where graphics and vision meet at the intersection. Because nerves and things like that.
Yeah.
Huge models. One of the guys who's working on that project is also working on a cross-view matching problem. So like GPS denied environments, can you figure out where you are?
Okay.
Then myself, another, we're mostly working on machine learning, just general machine learning with vision applications, so like space image classification, things like that. And then some of the master students, I do have some more interesting problems, such as like image reconstruction of like symbols from the 16th century to determine who published this book or whatever. That's actually a pretty cool problem.
Yeah, that sounds cool.
So more or less, yeah. But our advisor is really adamant about working on non-visible light, which the research community just doesn't care about, like CVDRs and things like that. So like, anytime I get the project, I'm like, okay, let's like solve the RGB problem first, please. So I can ideally get a publication out of this.
Yes, I would like something for me and something for you.
Yeah.
I'm working with Topus, and
he does,
yeah, but he doesn't really have any other graduate students right now that are working on it.
Oh, really?
Yeah.
Interesting. Oh, what is he now? Straight up there, right? Yeah. Really good track record, though. Like ECCVI, CCVC. I was going to ask him to be my minor advisor. When I asked him last year, he's like, no, bro, I'm on sabbatical. He's like, I was like, okay.
Yeah.
So he actually pointed me to Jason. Because he does, Jason does vision stuff, but he's mostly a machine learning guy. But I kind of would rather it that way almost.
Then the other way around.
His probability is just so strong. And like I envy that of him. He's just so knowledgeable.
Okay, you just look at the propositions and be like, oh, I think it's missing this.
Yeah.
It's definitely
Yeah. I was like, oh my gosh.
You know, like, okay, I guess I'll go reread that one section in Bishop about information.
Yeah,
theory.
seriously,
Maybe this
right?
time it'll stick.
But he went to Brown, and Brown has some very strong copyright theories. Never thought he went
You
to
probably
US.
have to like sink or swim.
Yeah.
Okay. Oh, shit, it's right. Let's see if we have it. Coming on here. Okay, any questions about homework 3 that was due by you should submit. Yes, yeah. Yes, everybody's okay with this?
Quick question. When did we decide the midterm was going to be?
I think the 26th,
Okay.
if I remember right. Was it next Thursday? I
Oh,
think
okay.
next Wednesday. So we'll have next Monday for bit review. And if my memory serves me. Okay. And I'll send previous midterms that I used back there. Okay, there is a whole zoo of using texture to change normals, and it is branded for different ways. So there are a few, and I made a bit salad, and I probably made a salad today now as well, but let's remember roughly what is happening. Bump map historically was the oldest, and bump map said you are looking at the surface which is, we think about a ray that hits a surface as a perfect sphere, or we think about a ray that hits the surface as a perfect plane. As a perfect plane. Here is a ray that hits, and we are absolutely sure that it hits a point P. Bump map says you are still allowed to change the normal, but only at the point P itself. So once again, this is a plane H, or this sphere, let's call it H for uniformity as well. But the way that hits P over here, that's the point, say, just below it. That's a point that I'm associated with this. And at this moment, in real time, except that it wasn't really used historically, wasn't really aimed to be in real time, I will start to compute what is a normal. I'll associate some arbitrary point, let's say the point just where I hit with P, and actually all I think about P and checking what is the difference between P, let's zoom it out, here is P, here is P of I minus 1, P of I plus 1, I'll just draw it in 2D, and if I'm just using the surface itself, and let's say that this plane is completely horizontal, then the elevation of the three of them is the same. Bump map says, I can still change the normal, but for this you need to compute in runtime, and the runtime is not important for the algorithm. The runtime is important for the historical context. Maybe in runtime, I need to ask what is the normals that the surface itself gives me. For example, if the surface itself is horizontal, then the elevation of the three are the same. If the surface itself is still diagonal, pi plus 1, pi minus 1, then I'll get the same delta. But at this point, I'm going to the bump map, which is given as an RGB values. And I'm saying I'll look at the R, for example, for pi, and I'll move it by the delta up or down, depending on what the bump map told me. The same goes for pi plus 1. It will have a different delta, which it will just be the red color. Similarly, for the green color, I'll look at the difference horizontal in the third direction, and now I compute the new normal. So if I just have one parameter, that tells me by how much to change it. And that would be the bump map. What makes it slow? Suppose you need to compute these normals at real time, which was a big deal when it was introduced, so it wasn't for any interactive applications. But still, the complexity doesn't care about the same number of triangles, and there is no occlusion here.
When we state that we're using the points pi minus 1 and pi plus 1 here, are we just getting the gradient using like a...
Exactly, yeah.
Okay.
So instead of using the exact gradient, I'll take the gradient, but change it a bit based on the bump map. And I'm not sure, maybe it's my ignorance, what is where displacement map and bump map are different than each other. Like I said, there are gray area and part of it. They sound to me like more branding than good reason. But so two issues. We are saying the moment we don't care about occlusions inside this surface. This surface cannot occlude itself, and I'm absolutely sure that my ray hits this very point. That's a distance. If I have a light that emerging, the light will fall on P itself. It's just a normal that I'm playing with. Yeah, and the next step was people said, hey, why wouldn't I compute these normals ahead of time? And you can, and basically you need to compute a normal base per each direction, per each pixels based on the approximated gradient at this point. Just look at the pixels before and after. Okay, yeah.
Can you go back to 2 slides, I think? Yeah, this one. When it shows the arrow going up, so are we changing the surface or are we only changing the normal?
We are only changing the normal.
Okay.
That's
so it only affects like the shading, like diffuse shading and stuff like that, without actually changing the normal.
All of them just do. Yeah, there is also the occlusion. Absolutely.
Okay.
Yeah.
So for the third one from the top down, it seems to suggest that the surface is being changed so that the heights change. Is that actually what's happening?
Yeah, but I don't change my opinion about where my ray hit. At this one. The next one I will. Actually, next one.
Okay.
Next one I will change my mind where the ray exactly hit this point. Yeah, so computing the normals in real time is hard. So the next part would be, let's give you directly the normal version at each point. And actually for the bump map, I could have just given that. I made a mistake. For the bump map, one color is enough. It's a grayscale level. It's just deformation of the X and Y. So one color would be enough. Bump map, on the other hand, normal map, I do give you by how much per each point, by how much I want you to change the normal on the X direction, and by how much I want you to change the normal in the Y direction. And X and Y is actually in the U and V coordinates, because your points might be twisted if you think about the texture. So, but I'll give you two colors that tells you add something to U, add something to V. But still no occlusions. Still the point, I don't care about these colors. A normal map, by the way, doesn't need to make sense geometrically. It can give whatever values that I want. It doesn't need to, connect based on surface that makes sense. Next part is asking, can I create occlusion between the surfaces? But not here. Yes, in the original world. In the, can I show you that part of this stone is exposed to you, part of the side of this stone. Brick is exposed to you and part is occluded for you. And that's where the parallax shading starts to be useful. Displacement shading, parallax shading that says a ray that hits the surface. I think that the surface is actually above the triangle or sphere that I hit. Let's say it's triangle or polygon that my ray hit. That's just a starting point of a ray. And where this ray really hits might be far away. Not very far away. Like, I will not necessarily worried about a ray that is completely coming as a gazing angles. Like, can I ask if this bump occludes 5 bumps ahead of time? Or if I find a point along the ray that is already inside the surface, displacement surface, do I wonder if that's the first point where it hits or not? So there are nuances, because grazing angles, well, you're basically running almost to the problem of completely hidden surface removal just on this terrain. Right. So I want to say the moment that I realize that my ray hits any of the bumps, so maybe I didn't say. So we will start by giving as the input, similarly to where we started, to the bump map, we will move the depth of each point by some amount. With respect to assuming that you placed a plate, completely planar plate of glass on top of this wall, and now I'll give you the texture will be how much do I move with respect to each one of the bricks. What's my gap, my vertical gap over here. And a ray that hits this sphere ahead of time, I will say I will follow this ray until I find out that it's inside the surface. What is the surface? How do I create the surface? It's the original glass, the original plane that was here, deformed, diffused by what the texture gave me, by how much to diffuse this point. So it needs to make sense geometrically. And I'll track this way until I'll find the first intersection point. And here there are a few nuances about how further away should I go. And that's, of course, much slower. It's very simple ray tracing. What you're not asking is, will my ray ever leave the wall and go elsewhere? You're just asking, what is the first point that my ray hit? And now I still have the problem of compute the normal at the hit point. Don't pre-compute it, but the important thing is that you need to track the ray, and that you can do in kind of a merge sort. Ask among the pixels, oh, it's important. These hills that you see over here don't have to be small with respect to the pixel size. It's fine, they can be quite large. You can push tons of information into the texture and care very little about the complexity of these guys. Where will it be helpful? If I have lots of objects on the table that are, bear with me a sec. If I move a lot of objects over these tables and I can see them from multiple images, probably the question of what is the first object that I see is very much view dependent. Here is a good different example. Here is a normal staircase. Building, normal staircase in the building. Here is my eye, and I'm asking what is the first, these rays that emerge from my eye, what is the first staircase that I see? And I care very much that, call it S1, partially occludes the next part of the next stair, S2. Part of S2 is visible to the eye, part of it is occluded by S1. So I very much care about this way. Where does it exactly hit? And once I have the location and the normal, and the staircase doesn't have to be small, it can be quite large. What's important? That if my eye is here and barely grazed through an object, there are no gains of this guy might partially occlude the one guy further away, or we just ignore it. The ray tracing part of this is done only in the neighborhood of the ray itself. Okay, with a few details that ask about good guesstimates about, because this is essentially a continuous surface, so you need to approximate it somehow, or describe it by a big set of pixels, which allows you to ask, hey, let's do binary search, for example. I'll shoot along this way, I realize that Q is inside my surface, where I entered the plane. Q prime is outside the surface, and now I can do binary search, for example. But I will not worry very much if I found out that that's a staircase that I hit and it's nearby where my ray hit the surface. I will not be very worried about maybe an earlier stair already occluded it, and I'm completely off. Yeah.
I have two questions. The first one is, if you're looking like parallel or slightly slanted above, you won't ever hit the surface, but you might hit the bumps. So is there a way for us to calculate the hit points in that case?
Yeah, that's exactly what we're doing. The thing starts to fall apart when I'm completely in a gazing angle to this virtual plane that I'm putting on top of this. Because now, if there are not all the stairs in the same height, then I might run into problems. If I say a stair only occludes part of the next stair, which means my viewpoint is not very much parallel to the wall, it's kind of reasonably enough to the wall, then definitely you are essentially doing, or the GPU, that's the beauty of it, by the way, it's all done by the GPU and all supported by WebGL, OpenGL. You are basically, from the eye, you're shooting multiple ways, or do your Z buffer projection, as you're doing homework for, and just ask for a ray. First, where did I hit the surface? I notice that I hit the surface of the staircase, which now completely removed from the game hitting any other object, so no hidden surfaces between any other object. All these rays hit the plane edge of the staircase. Now I want to find where exactly did they hit the staircase itself, and staircase is simple enough, or wall is simple enough, that I only need to check the surface in the vicinity of where the ray is hit, topology, yeah.
So what I'm saying, so that surface on the slide there, is it actually the three bumps, or is it just the surface, like the flat surface, with the normal map and the bump maps that create the bump?
Good question. My algorithm first says there is other triangles living in 3D, other polygons. I use my Z buffer to first determine here is a portion that is occupied by the staircase, and here is a point where I start my search. And now my fragment program should start looking, or the OpenGL to start looking just at the neighborhood of the vertex. So it's kind of CPU-like algorithm. So, and yeah, and once you found the exact hitting point, P, you will ask from this hitting point P, what is the distance direction to the sun, what is the normal, which I have to compute the nearby point. Yeah.
So can this type of mapping support like structures that are off of the surface? So let's say this right here is my plane. Can I have, like, you can have like surfaces like this, could you have something like above it, or does it have to be connected to the surface?
My understanding is that it needs to be two different surfaces. It might be fine if you think that it's all connected and I can build it all as a terrain. So if I describe it from the side, so the plane, other people didn't see your gesture, so it was one big surface and something that falls above it, I think that you'll run into troubles because array that goes from, just my hand without the arm, is the other surface array that comes from here. An array that comes from here will occlude this part, but this way will hit this part. So I'm not, you can probably refer to it as, I don't know if you can assign it to be transparent pixel, so that might be. I will try to come up with better answer. Okay. So many variants of it, very hot topic, different methods of texture. We are still in the texture, by the way. And of course, the gating angles. Yeah, so all of it allows you to do all the beautiful aspects of having specular reflections, very nice games of lights at each individual point, despite having it only, the whole wall here is one surface, plus the texture that just be the distance, the deformation. Okay, let's talk about, before moving to the next topic, let's talk about bilinear approximation. Bilinear approximation, that we kind of mentioned it, but let's mention it again. Let's say that here I have Q1, I'll wait with the other two. Q1, Q2 would be 2 pixels, and I have 2 centers of pixels, so actually the pixels take all this place. And now I found an array, or I want to render a point P, or I want to copy it from one image to another, a point P that is somewhere between the two center of these 2 pixels. So P here is a center of a pixel. And you actually went to this problem already in homework 1, where P was the center of a picture that was a target, center of a pixel, that was a target, and Q1 and Q2 was 2 input source pixels, or Q1 and Q2 here can be center of text. Center of textiles, which are, hopefully I mispronounce it, don't mispronounce it. It's just pixel that belongs to a texture. Right now I'm back to the case that texture is just an image. So a pixel of the image is a texture. Am I right? But good. Oh, so I want option 1, let's decide that Q1 gets a color of the nearest object, nearest pixel. I have the texture, I have all the center of the pixels over here, and that suggests the aliasing, because the moment that one of the images moves a bit, then looks at this point, it now gets a color of gray, and once I'll be able to move the image a bit, move the image by tiny bit, and suddenly you got a flickering effect. So the moment that the viewer moved a bit, we run into problems, and then we need to decide about aliasing. So linear interpolation will say compute the area of, let's call this part Tx, and decide about, similar to barycentric coordinates, we already played with this, about T1, 1 minus T1 times Q1 plus T1 Q2. Q1, Q2 here will be the RGB or any other property that belongs to this point. And that's just linear interpolation. But T is just what a distance from Q1 until P. If P happens to be completely in Q1, then T, it's T sub X. T sub X is very small. 1 minus T sub X is almost 1. All the way it goes to Q1. If P is all the way to Q2, then I'm just giving all the way to Q2. And if Q is just at the middle, then you blend between the two. So that's linear interpolation. But normally P will not be just between 2 pixels, but will be between 4 pixels. Black, 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 black. Let me zoom out, please. So here are my 4 pixels. Here is Q, and I want to create linear interpolation similar to the barycentric coordinate, but now I'll use what's called bilinear interpolation, which would tell you the following. Draw a vertical line through Q, through P. What was the letter that I used before that? The center of the old pixels of the texture was the Q1. Here is the point P where I'm just want to find out what is the interpolated color. Look at P1, just horizontal with Px, Py, and now P1 is this value. Look at P2, which is between Q3 and Q4, and P2 would be 1 minus Tx, the same Tx, because it's vertical. 1 minus Tx times Q4 plus T4 Q3, the very same formula. That gives me the linear interpolation of these two guys. And now I'll look at the value of Ty, and I use linear interpolation between these two guys. between P1 and P2. Which essentially, when you open it, start to look like something that involved Q4 times Tx times Ty. So you have the multiplication of these two parameters plus Q1 times 1 minus T1 times 1 minus Tx, 1 minus Ty, and so on. So you have just giving weights to the four numbers, or how would you think about it if we want to play with area? Expand the barycentric coordinates.
So they tried in here.
But I want to bring all four of them into the game, and they form a perfect rectangle. So here is my point, P, and I want to say that the total combination would be, why am I obsessed on the word? That the RGB of Q, I drop the RGB of Q, equals to W1 Q1 plus W2 Q2 plus W3 plus W4. Q4 give the four guys a weight, and the WIs are all positive and sum up to 1. That is a convex combination, as usual. Okay. Yeah.
So could you just draw another line going, like horizontally like that, and then the weight for like Q4 would be the area of the opposing rectangle?
The area of Q4, counterintuitive, you see four triangles. The triangle that is opposing, that's right, that's a term that I should use. Opposing sounds good. The other rectangle, look at the area of this rectangle, divide by the area of the big rectangle. So let's call it R4 over here. So W4 equals to R4 divided by area of the Q1, Q2, Q3, Q4. Make sense? The relative area of it. And for Q1, the area would be just the area of the opposing triangle, which is, if this is 1 and this is 1, what did we say the weight of Q4? The weight of Q4, based on this formula, was what? Weight of Q4 was T1, no, yeah, so Tx was, that was Tx, and that would be Ty, and based what is a weight of Q1, it will be Tx times Ty, based on, no.
Weight of Q3.
Something like
The weight of Q3 will be Tx, Ty.
the weight of Q3 will be Tx, Ty, and the weight of Q4 would be
1 minus Tx times
1 minus T. Okay, so I was wrong about this weight. But the weight of Q4 would be 1 minus Tx. So the W4 would be Tx, Ty.
4 is 1 minus Tx.
4 would be, let's see, 4 weeks, so yeah, y
1 minus dx times t.
1 minus dx, 1 minus dy. Okay. And so, I'm a bit shaky about this, but yeah. So that's a bilinear interpolation, except that I cannot multiply properly now, but so that's bilinear interpolation. Yeah, forget about these slides. We can have accumulation buffer and stencil buffer. Not sure why this slide is here. It's related to the Z buffer. If you want to add the last few values, want to sum up a few values, you can use either the accumulating buffer or the stencil buffer, depending on how fast and how many bits each one of them have. We actually talked about it. It's related to what happened when we have a few objects with different transparency, which is still a topic that we need to cover, because the order matters. Right. Or accumulating buffer, another use. What's the difference between this and the Z buffer? That you can say, here is one image, here is what I have in the accumulating buffer so far, and I'll just add to it another image to all these points. And it all happens, as far as you know, in parallel, if your hardware supports it. Okay, so you can take a few images and create soft shadows using the accumulating buffer. You can take a few you can move one of the objects and create soft shadows instead of hard ones, and so on, by just a few parts. Let's talk about mip-map, which will tell you why I'm talking about this part right here. So let's say that I have an object that sometimes I need in full resolution, and sometimes it's far away, so I can get away with much smaller resolution. So this is a less important reason that I use mip-map. So the idea of mip-map would say, take the original image and don't get rid of it. You do keep the original texture. But also take every 4 pixels in the in the original image and merge them into a single pixel. For example, by taking the average color of these 4 pixels, which will give you the image with quarter the number of pixels. Right? And then do it again with even a lower resolution. Why is this a good idea? Because maybe I don't need to waste, if it's very detailed, but it's also far, far away, I don't need to waste so much time if I just pick the right resolution satisfied for the user. You'll see more about it in the next slide, and I can get away with the level of details that I can get away with. If it's far away, don't waste time for all these pixels if they are all sub-pixels size to the user. They don't matter that much. If it's far away, use much smaller resolution. That is, you are taking the image, merge every 4 pixels. It's not a sliding window. The first 4, 2 by 2, merge. Next 2 by 2, merge, and so on. Takes average, yeah.
So this map would be pre-computed, right?
Yes.
Okay.
And by the way, OpenGL will do it for you. Just tell it that you want mip-map. So that was one reason to do the mip-map, yeah.
So like so this is like a situation where, like specifically in the context of rasterization, this makes sense. But if you were doing like a ray tracing with our billboards, it doesn't really save you anything because the lookup time in an image would be the same.
Yeah, I agree.
Okay.
That's not the point that I'll use it. It saved me a big time, but it brings us to an idea that I couldn't control myself, so I also mentioned the whole level or the whole idea of let's keep the same model, the Stanford bunny, simplified it, merge vertices, lots of algorithms that describe how to take a very detailed set of polygons, triangles, and get rid of, say, every few of them, stay away with much fewer triangles. Do it again, do it again. If the bunny is far, far away, just use this part. This definitely with normal map are perfectly fine to make it look smooth. If the bunny is very close, get a higher resolution. But you're using all the pixels, and on the fly you decide which one of the levels you are putting there. For example, based on the error, based on how important it is in the game, and so on. At which angle do you see it? Yeah.
So for the one with 76 polygons, I think the ears are a single triangle. Does that mean that if you had the like you see that for 76 looks like the ears a single triangle?
Yeah.
So if it happened to be facing the wrong direction, would it be occluded because of the
Yeah, I did not speak about yeah, that slide is slightly orthogonal to the discussion about the texture. Here I just took advantage of, let's keep we have a very complicated model. We can keep different resolutions of the model of it, multiple copies, which sound which one of the models should be used? Well, we decide about it in real time, depending on the camera parameter relevant at all, how far away from the viewer, and so on. Does it mean that the ear here is just a single triangle? Great question. Does it mean that the ear will look like a single triangle when you render it? Trick question. Bring us to old material.
Depends, right?
Go on.
Well, it depends, like, what kind of textures you're applying and things like that. Shading.
Shading. But it doesn't need to look flat. Well, it's to still be triangle, but you can give it the feeling of curvature by, even without any texture, by using, help, review for the midterm. Diffuse shading, and diffuse shading here takes a triangle and look.
The blend fong or the fong shading, where it's like to gap the rolls.
Remember, if I have this sphere, Fong algorithm says compute the actual normal, compute the average normal at the vertices, weighted average, because usually a vertex has more than two normals than its neighbor. And now, as you're walking along this triangle, you're changing the direction of an approximated vertex. If it's a triangle indeed, then you'll use barycentric coordinate. If it's a quad, then you'll use something similar to you could use something similar to the bilinear interpolation. But, and actually there is a mistake in it. It sounds like if I need a lot of memory here, which means lots of time to render it, time to bring it to the memory and back, sounds that I need to take this volume times, if I have log 2 of n many levels, and I start with 70k polygons, then it sounds like log k, say, I'll keep 10 levels over here, going from 1000 to 1, 10 levels, log to the base 2, reducing the amount of level by 2. So I move from 70k polygons into, if I sum up the memory in all of them, then it's log k time, then it's 70k triangles times log 2 of 70k, making it, say, 10, giving me about 700k, which is absolutely the wrong calculation. There is an overhead of memory, but I don't only keep this value. I keep this number plus this number plus this number. Meaning that I keep altogether, if I have 70k triangles, it will be 70k times 1 that I store for here, sum, plus maybe I get rid of half of them. So it's 70k times half, plus 70k times 1/4. So, and this sum, even if I go all the way to infinity, this sum is only 2. So this is way too pessimistic, and the actual number would be at most 2 times 70k, many polygons. And once again, it's not the main reasons to use the meat maps, but what should be the right summation in the case of the meat map?
What are you saying? Only up to a certain number of terms?
So the deal about this is that that goes to infinity. That's I don't care about it. That's a very tiny mistake. It's almost immediately if this part was correct, but this part is wrong. In the case of Midman, yeah.
It should be 1 plus a fourth plus a 16th, then dot.
Yeah. It's much smaller, but it's 1/4, because when I merge two 4 by 4 pixels, these 4 into 1 pixel, I get rid of 4 of 75% of them, and then the next one would be 4 squared, 16, and the next one would be, help, 64 times 4, 4, 16, 64.
Yeah. My confidence in powers of 4 is
yeah. Okay, so let's see why do I need maps. So it's actually much smaller than 2 over. It's barely. But that's back to texture. That's less of the issue of why we need the meat map. Here is a big issue with the meat map. That here is how I want this surface to be. That looks once. Here is how the surface looks like if I use texture. Normal texture, you'll see it's just a chessboard, pretty much, just a grid. Let's see this example of this grid. Next picture, it's just part of this grid that keeps repeating. Okay, and once I'm actually moving a bit my view, see what's happening here? That all these pixels in the far away are jumping from black and white, black and white. And that's why. That's because we look at the signature of each pixel in the texture. 1 pixel, what is equivalent to if this pixel is around 1 pixel of our screen is in the same size of 1 pixel of the image, there might be a bit flickering, but it will be less than it. Definitely, no, it will not happen if I have many pixels of the texture, many textiles inside 1 view pixel. It shouldn't jump too much. The problem starts when we have 1 pixel that we project. We place the texture, 1 copy of the texture after another, and suddenly, where is the boundary of a pixel? That's an excellent point. Remember that a pixel is not just a point in the center of a pixel. It's a rectangle with an area. It has an area in 2D, and these pixels of the image, if it's far away, contains many, many textures, and they can be arranged in some strange way. Okay, so what is a color that we can do, or how can we prevent this obvious aliasing? By the way, yeah, that's aliasing, what we saw in this image. We will say if the images are far away that we get to the risky part. Risky would mean the moment that a texture, the size of a texture, is comparable to the size of a pixel versus 1 pixel contains a lot, one the opposite way. I take it back. If here's my image, here is my, say, texture. That's one texture. But one pixel that one texture covers many pixels that you see, that's a good thing. Because it means that it will, many of them will have the same color, and if you move a bit the image or the viewpoint, then just on the boundary it will change as expected. That's the normal part. Why is our opposite part? Ask for troubles.
Is it like the relative pixel densities are what we're going to use?
Essentially, these pixels that I need to assign one color contains many different textures, and they all have different colors. If I use sampling, then I ask for troubles. Move the image a bit, and the sample point, the center of the pixel, might fall just by tiny little perturbation to move from white to gray. Okay, so as long as one pixels, one texture contains many pixels, we are happy. The moment that one pixel contains many textures, we're in troubles. Then sampling, ask for troubles. What would be better? Bilinear interpolation. But you will still have the issue. Here is a signal where each pixel is mapped to. And suddenly inside this one particular pixel, you have very strong image. So now in real time, you want to average all these pixels. Or not, or do something smarter. What can I do instead of, in real time, average the average color inside all these pixels? Pre-prepare an image with all these pixels. Well, I may be cheating, but if I have an image with all these pixels already summed up, then I just need to bring up the average value inside this region. But the average value inside this region is more or less exactly what I got, what I stored in this image over here. Zoom out this image just a bit, and what do you have inside each pixel? Right here is the tiny little model. You have the average value of the image pixel in some area. So the areas don't exactly align, but it works. It's much better, and that's the main one of the main advantage of MIP maps. Okay, so, and now, do you need to think, yeah?
So, can you go back one slide? If we're using MIP mapping, if we are finding the image for that pixel over there, but then we move it to the right a little bit, how do we know to use which MIP map texture or something? Because, like, if we are putting the pixel on the left, it's going to be much denser. If we put it on on the right, it's going to be less dense. Then how do we know what to show, essentially?
So you will take 2 pixels. You'll first find the right level in the map. The level at which pixels is roughly the same side of the texture, which is an approximation. The pixel usually will not be square shaped. It's not necessarily the axis line. But we'll find the right reason. We will use by linear interpolation, even in the correct level of the mip map, if we just hit one of the levels that are stored in the mip map. Again, if we just store the right level of the mip map, we will take the 4 neighboring pixels. We have a slide for it. Find the correct level of the pixel size, and do the bilinear interpolation of these 4 pixels. That if you just hit the correct level among the images that are stored in the mip map. Usually you are between levels, so you will do a linear interpolation between the 2 levels, one that I got from level I and one that I got from level I+1, and now I'll do linear interpolation. Which brings us into trilinear interpolation. So sounds like tons of work, and we need to decide what's the right level, or ask OpenGL to use mipmaps. It's all built into OpenGL. And OpenGL will actually create for us the various levels of the image itself. But we can do even better, because even if I want the average value, the average value of these pixels along this part should be different than the average value of about this part. Right? You still have, what are you doing over here? You are averaging on this direction, but you are more or less accurate in some direction. So let's bring us, and where do you run into problems? Over there is what happens if this 1 pixel that I need to average actually falls on a bunch of blue pixels. Let's go back to the image of the wall. Sorry. I lost an image, sorry. Yeah, so let's even look at this part. I want to average it for a pixel that lies like this. We'll have remember, that's a footprint of one individual image that you want to see. And if I'll just move it a bit in this same direction, I need to get a different average. So if I'll just do the averaging, I will not notice that this part is much bluer, the next row is much blacker. Instead, I will still do the averaging of everything that happens over here, but I can also ask OpenGL to average this part, and this part, and this part, and average this, say, 3 of them in a direction that I'll specify, the direction, say, from the user, direction from the eye. All I need to do for it is to say I want to turn on the anisotropic filtering, one of the flags that you can tell OpenGL. Of course, you are paying for it in time, but it's not as bad time because it's all GPU processed. And GPU texture is such an important part that texture and GPUs are already quite optimized. I just describe it as part of the, let's take the weights from the rastering process, the barycentric coordinate, and look into the image as a look into part, but the texture part is optimized to much higher degree. Okay, so all you need to do is just to understand what's happening and why is this needed. Again, had I kind of solved the anti-aliasing here, saying that that's the right resolution, but if I want to average, I don't mind that much averaging in this direction, but taking a few in this direction, but if I'll average like so, it will look very blurry. If I still want it to look sharp, it needs to be averaged of a few pixels in this direction, but keep it different than the pixels on the orthogonal direction. Anisotropic tells you here is the critical direction that how do I specify that don't average. In this, I don't want to average in this direction, but I do want to average in the direction that I specify. Okay, moving into next topic, which is various trees and data structures. And I owe you a bit introduction to how to use WebGL or whichever software that you prefer to use, but with everything that but with something that gives you everything in the GPU, which means flashing into the GPU. I just don't know, but I assume that there is similar support to OpenGL and WebGL in Python, if that's your language of preference. Handle it, but I'll try to learn a bit more before Wednesday about Python. And so, topics that I'm talking about almost every course that what's happening? Almost every course that I'm giving quad trees, R trees, and geometric hashing. So I'm shooting a bunch of ways. Oh, wait. I want to shoot a bunch of ways. I want to see what are the objects that are near me, certain distance away from me, and let's say what are the points, let's make it points in the moment at distance less or equal than 1. Some fixed distance that I care, that I decide that's close to me. And I'll do my first attempt of ray tracing or the buffering only among triangles that has a vertex that is close enough. So that's where you are checking for other players if it's multiplayer scale. Or that's where you are checking for hitting obstacle. Okay. So I want to describe an algorithm. If you have not heard me talking about this course already, I know that some of you have. Let's find a data structure now. So I want to describe a data structure that will help me find all point in its vicinity, and vicinity here is defined as distance 1. And among them, you, depending on the application, do some further filtering. So let's see. So let's remind everybody what hash function is. I'll define, say, age of x, where x is an int. And what I'm planning to do is to use a hash table. And in this hash table, I'll assume that there are only m cells, 0, 1, all the way up to m minus 1. And I want to map every key x. X here, I'll assume that it's in integer and it all lives in 1D to start with, and down from 1D to 2D. And I want to match for every x one cell in D. So insert of x will be done by insert into the table, which cell, the hash value of x. And so I expect the hash table to return int between 0 and m minus 1. That is, whatever you spit out, it needs to be a legit index or legit index in the table. And x would be in this place, or from this place I'll keep a linked list of all the objects that I wanted to put inside this cell. So many different hash functions. Simpler would be, for example, do age of x equal x mod m. M is 5, only 5 cells, and it will go 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on. What are you hoping to get by the hash function? You want to say, I want the same or number of objects roughly to fall in the same cell. If I have 5 cells, I want it on average, getting into too many details, on average in every cell, I expect to find 1. Some cells will contain 2, some cells will contain 0, but it will be very bad if all the numbers that I map into it will be mapped into the same cell. And a good hash function should not do it. So using modulo sometimes work, depending on your data, especially if m is prime. It's sometimes a good idea, kind of suggests more fairness in the system. Don't take, on the other hand, for some number of keys, maybe if your last digit in your student ID is a control group that says at which department you are, then modulo will just give me the last digit. That doesn't give me the same distribution. If I take the 2 digits, then maybe there is more personal information, but still out of, say, 100 cells, I only hit 10, and all my data will be in the same one. Let's write down a better hash function. If x is a float, I'll take x minus the floor of x, which gives me what? If x is 3.14 minus the float of x, then I'm getting just 0.17. Take this number, multiply by k, some strange and big integer, and out of everything that you're getting, do, of course, at the end, always you're ending with mod m, so the number that you're getting is a legit index. And that's normally considered better. That's what essentially you want is that as long as I'm changing anything in the key, I'll have a good chance that it will be mapped into different places. And actually there are some variants into this table. You can do much better than what I just wrote, but started good. Okay. Now, back to our geometric problem. So I want to know about objects that are distant at most 1 from me. And here is a grid of size 1, edge length of 1. And here is one of the points, Pi. And what do we know about x of Pi? Pi lives in the cell that, let's say this cell has the left corner of 0, 0, and the right corner is 1, 1. It gives me a pretty good idea about every point Pi should have x of Pi is somewhere between 0 and 1. So Pi and Pj are in the same cell if they are both have the same value. So what should be my geometric hash table right now? I will take, for example, and now I completely contradict the example that I gave beforehand. So I'll take, for example, as a hash function, take ax minus ax floor and do everything that I say about multiplying by k. So multiply by some big constant a. So now what I'll actually do is look at what would be age of x if I want to use it, or age of Pi. What I want for my hash function is to do the following. I'll give you a query point. If my query point lies here, here is Q, it's fine if you tell me that inside the cell of Q there is no other point. My query point is here. I want you to tell me that Pi and Pj are there. And hopefully you can do it in time that is linear, that is constant plus your output size. If you are reporting 17 points, it should take constant plus 17, because that's just the time that it takes to print all of them. So what can I do? I'll take age of Pi would be, for example, x of Pi floor multiplied by one constant, a, plus b times y of Pi, all of this mod n. And a and b are large constants. What do I get by this hash function? If I have some point Pi and Pj that are in the same cell, they will be mapped into the same cell, same slot in the hash table. And if I take Q, my query point, and apply the hash function of it, it will send me to the cell of the table. And the cell of the table might contain, here is another point, PR. In this table, if Q send me into this cell of the table, I will find Pi here, I will find Pj in this list. I might find also K somewhere in the middle, because the hash table is not one-to-one. Notice the grid it takes a moment to realize there is infinitely many cells of the grid. There's infinitely many cells of the grid, but how many of them are non-empty? If I have n points, only n of them are non-empty, and only these ones are actually represented in the hash table. And if you're using a reasonably good hash function, this will do just fine. And then you're saying that the chance that pk will be in the same cell is quite low. The access time will be roughly order of 1 to go to this cell, plus order of k, where k is the output size. And you can do some other tricks to validate it. Other points will not contaminate. So now you have a way to find who are the players that are near you, and that's a beauty. If unless you have a really bad karma, if the hash function works well for you, then on average it's order 1, which means that the chances that it's more than order 1 is actually going exponentially low. You're unlikely to find more than like you. There will always be some collisions, but the average number of collisions, if you're doing things well, is order 1. Like you'll find one other object in half of the times. That's where the math brings us in 5 minutes, or usually 2 meetings of 545. So that geometric hashing, that gives me who are inside my cell. I want to know who are in all the cells who are in distance away from Q, and I don't want any approximation. What does it mean? It means that I need to to check a few more cells, but not more than the 8 neighbors around me, even if I want to be very careful. What if I replace the close to me is not 1, but R, some other value R? The only change, and I'm all done, the only change here is that it's, where was it? It's x of pi, y of pi divided by R. And beside it, that's C. So that's the beginning of geometric hashing, but check out geometric hashing is a big deal by itself to find images similarity between shapes. Okay. Next meeting, quad trace and WebGL. Thank you.
Thank you.
Thanks.